Okay, we're continuing on here, chapter 15. We've been talking about solutions, and really towards the end, we talked about sort of solution stoichiometry, sort of where we left off. And remember, with solution stoichiometry, it really is, as we talked about, kind of the same steps as any normal sort of stoichiometry problem. Once again, we want to make sure we have a balanced equation. We want to convert to moles. We want to, if it's a limiting reagent type problem, make sure you figure out the limiting reagent. We want to then do the mole to mole relationship, and finally convert the moles to some other unit. The main sort of difference is with solution stoichiometry is really how we get to moles and how we oftentimes will sort of solve the final sort of answer. And it really does revolve a lot of times around molarity, which is our moles per liter. So once again, it's very common up front to solve for moles by taking liters times molarity, which is our moles per liter. Once again, you got to make sure, as we talked about, that you do convert the liters or the milliliters into liters, which is a common sort of conversion that you need to do. So unlike a maybe traditional sort of stoichiometry problem, where you go from grams to moles, which you can as well in solution stoichiometry, but a lot of times you may use the molarity to get to the moles and the volume. The other really major difference is really at the end as well. You may do a traditional maybe moles to grams conversion, but you may solve for something like volume, which would be our moles divided by our molarity, or you may in the end sort of solve for molarity as well, which would be moles per liter. So those are sort of the variations of it. In addition, you may even start the problem like a traditional stoichiometry problem, sort of grams to moles as well. But somewhere along the way, you are going to use something to do with molarity, volume, and moles as well. Once again, you can have a limiting reagent situation. And in this type of situation, if you, again, have enough information to get the moles of each of the reactants, then once again, you do need to figure out the limiting reagent. And really, again, the difference there would also be probably how you get to moles is, again, the molarity and volume, kind of using it to get there. So I think we finished last time on sort of an example. Any questions on those steps? So why don't we continue on? I think we've got another one to look at here. We want to calculate the mass of white solid calcium carbonate that forms when 25 milliliters of 0.1 molar calcium nitrate is mixed with 20 milliliters of sodium carbonate. So I'm going to give you some information here. And again, let's talk a little bit about the equation here to get you started. We are mixing calcium nitrate with sodium carbonate. And once again, you should recognize this hopefully as a double displacement reaction, where our positive guys will, again, switch partners. Remember that when you do predict what's on the other side, you want to get the basic formulas correct. So calcium and carbonate plus 2 minus 2 should give you calcium carbonate, which is a solid. And obviously our sodium, which is +1, and our nitrate, which is -1, will give you the proper formula here. So at this point, I'll let you pick it up with balancing it. And I'll give you some, let's see here, we're looking for the mass. So I'll give you some numbers. Calcium is 4008. Carbon is 12.01. Oxygen is 16. I don't know if you need it, but nitrogen 1401. I think that might be everybody there. And sodium, again, not sure you need it, but 2299. All right, so take a few minutes here, work on this one, follow through the steps we just talked about, determine how you should go about solving it. Okay, let's take a look, see how you're doing. So obviously, it's a stoichiometry problem. We worked on the equation here together. We do need to make sure that it's balanced, which it is not. So I think you just need to lay up a 2 right about there. And now I think we should be balanced. The next thing we want to do really is convert what they gave us to moles. And we also want to think about, is this a basic stoichiometry problem, or is this a limiting reagent type problem? And is this a limiting reagent problem or a regular one? This is actually a limiting reagent problem. The reason I do know that is if we think about molarity, which is moles per liter, if I am giving the molarity and the volume, I could get to moles, which means for this guy, I could get to moles. And also for this guy, I could get to moles. And that means that I do have the starting moles of both of my reactants. So again, even though it's sort of volume and molarity and all that kind of stuff, we can't get to moles. So this is definitely a limiting reagent problem. So we're going to still start it out the same. We're going to convert everybody to moles, but we do need to take that additional step like we talked about in previous problems to figure out which one is a limiting reagent. So to convert these guys to moles, remember that we do need to convert the volume into liters. So if I place over 3 places to the left, we will then times it by the molarity of our calcium nitrate, which is 0.1. Remember, the big M is moles per liter. So that is what the big M stands for here. Liters will cancel, and we will end up with here 0.025 times 0.1, 0.0025 moles of our calcium nitrate. We're going to do the exact same thing here for our other reactant, which is our sodium carbonate. Once again, we're going to convert our milliliters into liters, dividing by 1,000. Going to give us 0.02 liters. We then will times it by the molarity of our sodium carbonate, which is 0.150 moles per liter. The liters cancel, and that gives us 0.02 times 0.15, 0.000. No, too many zeros. We'll take out a 0 there. There we go. All right, 0.0300 moles of our sodium carbonate. First off, any questions on that calculation there? Obviously, you can do it all in kind of one calculation. These are, again, in terms of limiting reagents, this is our starting amounts of each of those. So just like we've done before, we're just going to choose one reactant and basically do a calculation to figure out, do we have enough of the other one to use it all up? So in this particular case, I'm going to figure out, do I have enough sodium carbonate to use up all my calcium nitrate? So here, moles of sodium carbonate needed. We would take our starting amount of calcium carbonate, which is 0.0025 moles of calcium carbonate or nitrate. We then would do a mole to mole relationship between the two reactants, which is a 1 mole of sodium carbonate gives us 1 mole of calcium nitrate. The moles cancel, and we do need 0.0025 moles of sodium carbonate would be needed. Remember that we're going to compare this to our starting amount of sodium carbonate, which in this case, we do have enough here in this case, right? We need 0.0025. We got 0.003, so we do have enough. And what that really means is our calcium nitrate would be our limiting reagent, and our excess reagent would be the sodium carbonate. Any questions on that? Remember that once you've determined which one's your limiting reagent, that is the one that's going to determine how much product you will make. So we'll come here and use the starting amount of our limiting reagent And this would be 0.0025 moles of calcium nitrate. Doing our mole to mole relationship between calcium nitrate and calcium carbonate. From the equation, it is a 1 mole to 1 mole relationship. Makes the math not too bad. And at this point, if I stop right here, I would be in moles of calcium carbonate, but we do want to know how much grams. So I'm going to calculate the molar mass of calcium carbonate, and the molar mass of calcium carbonate would be 4008 for our calcium, 12.01 for our carbon, plus 3 times 16 for our oxygen there, gets us looks like 100.1 grams per mole. Get that big 0.1 grams per mole. We'll just continue on with our calculation. 100.1 grams per mole of calcium carbonate. The moles will cancel, and we will end up with about 0.250 grams of calcium carbonate would be produced in this case, and that again would be your theoretical yield. Any questions on any of those steps there? Again, a lot going on, but it really does fall back to our basic stoichiometry steps: balance equation, convert to moles, figure out limiting reagent, mole to mole relationship after that, and then convert moles to some other units. So really still the same sort of 4 steps that we've done previously. Any questions on this type of stoichiometry? So again, you could have basic stoichiometry problems like we did, I think, the other one. You could have obviously limiting reagent problems. Again, the same rules apply. If you could get the moles of both reactants, you got to determine the limiting reagent. Any questions on that? Yeah. It is canceling out tonight. Right? You mean here, or? Are you talking about this stuff here? So this is on top, this guy, and this guy is on the bottom. So they are opposites of each other. So they're divided. Yeah. So we're basically taking 0.0025 times 1 divided by 1. And that's how they cancel out the calcium nitrate. And we end up with the sodium carbonate, I guess. Yeah. Yeah. Other questions? Okay. So let's continue on then. And let's talk about really another sort of solution stoichiometry problem. And it really is sort of what we did the other day and we'll do today. And these are sort of titrations. And neutralization reactions are often sort of what titration problems basically are, titrations that you do, especially with acid-base reactions. Remember that when you have an acid and it reacts with a base, you really do get 2 things. You get water and a salt. And a salt is an ionic compound. And really, water is a result of the H plus from the acid, the OH from the base. So in a strong acid, strong base combination, or in a lot of acid-base combinations, that's really where our water comes from. And that's why when we look at the net ionic equation, like we did when we were talking about different types of reactions, no matter what combination of strong acid, strong base that you put together, the ultimate net ionic equation is the formation of water. And if you remember, that is one of the reasons why reactions take place is to form water. So for example, if we took hydrochloric acid, say whatever base you like potassium hydroxide, so that's a strong acid, strong base. It is again a double displacement reaction where the water will be made from the H and the OH, and the salt will be made from the 2 ions that are left over, which would be KCl in this case. And if we wrote the complete ionic H plus Cl minus, is that is a strong electrolyte plus K plus and OH minus. Remember that we do keep water, anything that's a liquid, solid, or gas together, or a weak electrolyte. And we would break apart our potassium and our chloride here. Remember that the spectator ions can be found on both sides of the equation that look exactly the same. And in this case, it is always the salt that's basically your spectator ion. And that leaves you your net ionic equation, which we see here, which is our H plus plus our OH minus. Really, the formation of water is ultimately what is happening here and why they're sometimes referred to as a neutralization reaction. So when we did those titrations the other day, and again today, when you reach that equivalence point and it changes color, that's the point where you basically neutralize all the acid and the base together, and you basically have water there and a salt. So I think you have a picture. I don't know where my picture went, but as we did the other day, when we did titrations is a very common procedure that we use for acid-base sort of neutralization reactions. And in a titration, we basically add a solution of known concentration to a solution of unknown sort of concentration a lot of times. So we really do have a solution that we know pretty much everything about, and we have one where we really don't know too much about. And the way we do that is we use a burette like we did in class the other day. And remember, a burette is a long sort of glass tube, which the volume increases as you go down. You fill it from the top, right? It exits out the bottom. And then you would put something in here. So for example, what we did in class was we had sodium hydroxide up there in the burette, which is a base. And down here in the flask or beaker, you had an acid. I think you did HCl actually the other day. So you had your acid. We also put a indicator in there, if you remember. And for example, the indicator that we used was phenolphthalein. And phenolphthalein is colorless in acidic and base neutral solutions. But it does turn a pink color in basic solution. In fact, phenolphthalein, for example, works at a pH of 8.3 to like 10-ish. And around this part, it is colorless and gets gradually darker pink as you roll through the pH. So in this case, what we did in the lab, we knew the molarity of our sodium hydroxide, and we knew the volume of sodium hydroxide that was used for every titration that we did. From that information, we were able to get the moles of sodium hydroxide, just like we did in the previous problem. The information for the acid, we knew the volume of the acid we used. So we could use basically stoichiometry to go from moles of sodium hydroxide to moles in this particular example of HCl, and that would get us our moles of HCl. And now we would have the moles of HCl and the volume of HCl, and that would allow us to get to the molarity, for example, of the HCl. A titration problem really is nothing more than a solution stoichiometry problem, where at the end of the problem, you definitely use molarity. So a lot of times you do solve for molarity at the end, like we did in the experiment the other day, and we will do today. But when we do a titration, the goal is to continue to titrate. We'll use this example here. So you continue to titrate until you hit what is referred to as the equivalence point. And the equivalence point in an acid-base titration is the point where exactly the moles of acid will basically equal the moles of the base. So if you think about it, at that point, when you reach the equivalence point, all the HCl you started with is pretty much gone. All the sodium hydroxide that you added is pretty much gone. Really, the only thing left in the beaker or flask at the equivalence point is water, which was made as a result of that reaction happening. And you have a salt, which, by the way, in this case is a neutral salt. The sodium chloride is just basically floating around sodium ions and chloride ions. They're really not all that important. So when we do a titration, we do want to stop near the equivalence point, and you do want to pick an indicator that will actually change color near the equivalence point. So for this type of titration, or the one we're doing today, phenolphthalein is a good choice because it does turn color near the equivalence point. That's why we talked about trying to get the lightest color pink that you could get in a titration. And that's because if you do, it'll probably put you around this area, which is near the equivalence point, and you wouldn't be too far away. As some of you saw, it can be just one single drop, and it will go from like no color to dark pink or pink color and stuff like that. And the reason really for that is, as you will learn when you go to 200B or 1B, they call it here, I think. When you look at what's referred to as a titration curve, when you look at the pH versus, say, the volume of base that you add, as you start, say, an acid-base titration like you did, you have kind of a low pH because it's acidic, and as you start adding base, the pH starts to really rise, and eventually will top out if you continue through the entire titration curve, actually past the equivalence point. Your equivalence point would be somewhere in this ballpark. You get really basic because after the equivalence point, you're just adding more base, and that's why the pH jumps really, really high. So what happens in, say, a titration like what you guys did the other day and will do today is as you start adding base, so as you start adding this base, you're using up some of the HCl, and it's becoming more basic because you're basically adding base. But what typically happens in all titrations is as you approach the equivalence point, it will pretty much go pretty vertical. Yeah. And what that means is it goes pretty vertical in terms of pH. And that means that essentially you do not need to add a lot of volume to change the pH a lot. pH changes a lot between here and here, right? Say this is a pH of 7, and this is like a pH of 12. There's a very big jump in pH. The amount of volume, which is down here, did it take a lot of volume to change that pH a lot? It didn't, because it's going vertical. And that's why one drop can send you from a pH of around here, the equivalence point, to a pH over here. And what your indicator is going to show you is it's like now super dark pink because the pH is really pink because your indicator is 8.3 to like 10. So now you're up here and really pink. So that's why I said the other day, the color is not super important. You should try to get light pink, but the color is not extremely important because it's more the volume that you add. And if you do it really slowly and carefully as you're doing your titrations, you know, you will be okay, even if you're a little bit darker color of your solution, as long as your volumes agree between titration. And that's because if you're careful and just miss it by a drop or two, right? So maybe your pH is here or here. There is no significant difference in the volume in any of those parts. Now, if you're not careful, you just open up your burette and just let it go and go and go, not really doing a great job other than you just open it up and let all your sodium hydroxide, you could get that same dark pink color way over here, which means you have significantly missed your equivalence point volume by a lot. But if you're going slow and doing drops or so, they're near the equivalence point, maybe you miss it by 1 drop or 2 drops, it's not going to make a big difference in terms of the volume of the equivalence point. But again, if you're not very careful, that's why you can really overshoot it. And that's why instructors will oftentimes yell at everybody, try to get the lightest color of pink. So at least they have a good feeling that you're in the right volume for your equivalence point. But if you're really, really careful, the color's not all that super important. It really, again, the volumes agreeing are. And that is the reason why 1 drop will basically change the color a lot. Any questions on that? Okay, so let's take a look at an actual sort of titration problem like we got here. What volume of nitric acid is needed to neutralize 45.0 milliliters of a 0.55 molar KOH solution? So let's go through this one together. So we're going to start with an equation. So we have our nitric acid, which is a strong acid. We're going to add it to potassium hydroxide, which is a strong base. Once again, it's a double displacement reaction, acid-base reaction. So you should always know that you make water in this case. And again, that water comes from the OH and the H. The salt will come from our other guys coming together. So once again, here we do want sodium, potassium that's +1, and nitrate that is -1 to come together to make our equation. At this point, we want to make sure that it's balanced, and I believe we are balanced in this case, so we are good. The next thing we want to think about what they gave us. So we have the volume here of our nitric acid. We have the molarity of our nitric acid, and we're looking for the volume. For our KOH, we have the volume, which is 45 milliliters, and we do have the molarity. So we do want to decide, is this a limiting reagent problem? And the answer is a limiting reagent problem, because we could definitely get to moles from this guy, but we cannot get the moles from this guy because we're actually looking for the volume. So ultimately what we want to figure out is, if we think about the molarity of our nitric acid, which is moles per liter, we already have the molarity. We're going to be looking for the liters. So we need to figure out the moles of the nitric acid part. So what we're going to start with is basically converting our KOH into moles, because we definitely could do that, and that's sort of the second step that we want to do. Once again, we do need to convert our volume into liters. So we're going to take our 45 milliliters. We're going to convert it into liters by dividing by 1,000. And then we're going to multiply it by our molarity. Once again, I'm going to use both units so I can see it. Moles per liter of KOH. And this is basically like our second step in the stoichiometry problem, converting to moles. And if we do that, we end up with 0.02475 moles of KOH. Remember that we're not looking for the moles of the KOH, but we do need the moles of the nitric acid. So that is where the stoichiometry is going to come into play. So we're going to look at the mole-to-mole relationship between these two guys. And again, we happen to hit a 1-to-1. They're not always going to be 1-to-1, but we still have a good streak of that going. 1 mole of KOH gives us 1 mole of nitric acid. So that's kind of like the third step there in our stoichiometry. Gives us 0.0247 moles of nitric acid. Now that we have the moles of nitric acid and the molarity of nitric acid, we could use the molarity equation to solve for liters. Liters would equal moles divided by the molarity. So using our moles here that we just calculated, using the molarity that was given to us for the nitric acid, which is 0.15. And in this case, we want to divide. So we're going to put the 0.15 moles on the bottom per liter of nitric acid. The moles will cancel. Gives us, divided by 0.15, 0.165 liters of nitric acid. Or if we want milliliters, we would multiply it by 1,000, and that would get us 165 milliliters of nitric acid. Either one would have been okay in this case, since it really didn't specify. So a stoichiometry titration problem, which is what this is, and sometimes it may not straight up say titration, it may say neutralize. It's kind of a key that it is sort of a titration problem as well. It's really the same steps. Step number 1, balance equation. Step number 2, convert to moles. Step number 3, mole to mole relationship. And step number 4 here, again, sort of use the molarity at the end to get something else. Any questions on any of those steps there? Okay, so I think you have one more there to look at. So let's take a look at it. Or why don't you give that one a go? Let me see if I find it. I think you have. So look, doing the one that should say what volume of 0.5 molar sodium hydroxide is required to react with 125 milliliters of 0.5 molar. We're going to react with our sodium hydroxide, which is a base. Once again, this is going to be a double displacement reaction where we should know that we definitely do form water. And again, that is going to come from these two guys, which means the salt part will just come from the proper putting together of our other two guys, which is a sodium with a +1 charge and a sulfate with a -2 charge, which should give us this guy here, Na2SO4 as the proper formula. Remember, now that we sort of have the right formulas down, we can balance it. We're going to lay up a 2 here in front of the sodium hydroxide and a 2 there, I think, in front of the water. And I think we should be balanced at this point. First off, any question on how to write the equation there? Once again, we can kind of pull out the information. We're looking for the volume in this case of our sodium hydroxide. And we do have the molarity of it, which is 0.5. We do have the volume here of all sulfuric acid and the molarity. Once again, from this information, we really could only get to the moles of our sulfuric acid. And we are going to be kind of looking at molarity here of our sodium hydroxide, which would be moles per liter. So once again, we are looking for the volume. We do have the molarity given to us. So this again is where we're going to use stoichiometry to get to the moles of the sodium hydroxide. So we'll start like normal here. We're going to take the only thing that we could get to moles in, which would be this guy. We want to again convert our volume into liters, which it always needs to be in when you're using molarity. And again, basically move it over 3 places or divide by 1,000 gets us to 0.125 liters. Using the molarity with both units there, 0.5 moles per liter of sulfuric acid. The liters will cancel at this point, and we will end up with, bless you, 0.0625 if you get a number here. 0.0625 moles of sulfuric acid. That's basically kind of like our second step there in stoichiometry. We're not interested in sulfuric acid. We do need to get to sodium hydroxide here. So this is again where the stoichiometry part comes into play. And from the equation, it is a 1-to-2 relationship in this case, which again is why it's important to make sure you have the balanced equation. So continuing on with our mole from the equation. Then we'll cancel, and that gets us basically that times 2. 0.125 moles of sodium hydroxide. Again, using the stoichiometry part, that now allows us to have the moles, and we have the molarity of our sodium hydroxide. So once again, we could rearrange that and solve for liters, moles divided by molarity. Taking our moles in a dimensional analysis approach, using the molarity of the sodium hydroxide that was given to us, would be 0.5 moles on the bottom, liter on top. And here we would take that divided by 0.5, gets us 0.25 liters of sodium hydroxide, or if you multiply it by 1,250 milliliters of sodium hydroxide would be needed in this case. Once again, step 1, step 2, step 3, and here step number 4. Yeah. Any questions on any of those steps there? All right, so let's try one last sort of titration problem. Let's say we did a titration and we want to know if it took we'll do 35 milliliters of 0.25 molar calcium hydroxide to reach the equivalence point in a titration of we'll make up some numbers, hope for best, 65 milliliters of hydrobromic acid. What is the molarity of the HBr? All right, so take a couple minutes, see what you come up with. Again, still same sort of steps. Think about what's given, think about where you need to end up. And it probably should involve some stoichiometry somewhere. Yeah. That's calcium hydroxide, CaOH2. So you could consider this sort of a strong acid, strong base titration for this problem. We'll consider it a strong base for this reaction. Okay, let's take a look. So once again, titration sort of problem, solution stoichiometry problem. We're going to start with the equation. So we got a little hydrobromic acid. I got a little calcium hydroxide. Once again, it is a double displacement reaction, and our water here going to be formed from the same two spots. Once again, that leaves our calcium and our bromide coming together. Calcium being +2, bromine being -1, means we should end up with something that looks like this, which means once again here we do need a balance by putting a 2 there and a 2 there as well. Any questions on that there? At this point, if we take the other information from the problem, we are looking for the molarity here of our HBr. We do have the volume given to us. Here for the calcium hydroxide, we have the volume and the molarity given to us, which as we know, that should allow us to get the moles. We obviously cannot get the moles of the HBr, so that's where the stoichiometry part is going to come into play. In this case, though, we are looking for something different for the HBr than we did in the previous problems. We are actually looking for the molarity. So at this point, we do have the volume given to us. It's just in milliliters. So we do need to convert that to liters, and we would have the bottom part. So the top part here is going to come from the stoichiometry calculation part. So we're going to use the stoichiometry part to figure out the top part. And we will do that by converting this guy into moles here. So the first thing we'd want to do is, again, convert our volume into liters by dividing by 1,000. Going to give us 0.035 liters of calcium hydroxide, using the molarity of calcium hydroxide and multiplying it by it. Again, removing the big M and replacing it with both units so you can see it, moles per liter, which is what the big M stands for. So again, that is that. The liters here will cancel. That will give us here, my made up numbers, 0.035 times 0.25 gives us 0.00875 moles of calcium hydroxide. So we're into sort of like the second step there of our stoichiometry problem. Remember, though, that we ultimately want to get to HBr to get the moles. So that is where the stoichiometry part is going to come into play. And looking at the equation, we can see there are 2 moles of HBr for every 1 mole of the calcium hydroxide. So using the stoichiometry to get us to the moles that we need would be our next step, 0.00875 moles of calcium hydroxide. From the equation, 2 moles of HBr, which is what we need to find, has 1 mole of calcium hydroxide. The moles of calcium hydroxide cancel. Times that guy by 2, 0.0175 moles of HBr. And then that really is sort of the third step of stoichiometry there. Any questions on that? Again, the purpose of why we did that is really what we were missing here to solve for the molarity. We do have to do one other conversion, which is take our volume of HBr and also convert it into liters. Going to give us 0.065 liters of HBr. We now have the moles. We now have the liters. So the molarity of the HBr can be found by just dividing the two. Going to get us divided by 0.065. Not too bad of a number. 0.269 moles per liter. I'll write it up here a little bit better. 0.269 moles per liter of HBr, or you could just write 0.269 big M HBr. And again, this would be sort of the fourth step where we use molarity here, obviously the molarity formula, to actually solve for the molarity. Any questions on that there? So titration problems, again, really just stoichiometry problems that involve molarity of volume. And this is a very common outcome. This is really the calculation you need to do for the last experiment and today's experiment to figure out the molarity of your acid, I think, in each case. But like in previous problems, you could use solution stoichiometry to figure out grams or volumes. So again, that's just sort of the major differences. Any questions on solution stoichiometry, titration problems, any of those things? Okay. All right, so I think that is going to be it for this chapter, I think. All right, I think it's a good place to lay it up, I think.